not want to have a... Okay, we will start.
Very nice, really inspirational.
Okay.
What has happened to the HDMI cable?
Yes. The cable.
Should I? They have HDMI cable? No. There was an HDMI cable before.
This one? This one? This one?
No, no.
This one? This one?
No.
Yury is Yury.
No, okay. I will bring another one, yeah. Okay. No. Let me just take another connector then if we are switching to VGA. Okay, yeah, seeing the box, yeah. Is it there?
So, let's move on. Thanks once more to our previous speaker, Adam, for being so perfect with time. So, thanks a lot once more for that. So then, we move to the next lecture. The next lecture will be given by Yury Gogotsi from the Drexel University, and I want to add some few comments to his brilliant work. And I'm saying that we were already hearing that Professor Yury Gogotsi was a part of a team that discovered a new family of two-dimensional materials, carbides and nitrides, MXenes are called, that they show exceptional properties, they say, for energy storage. So this means that I really hope that this potential will be shortly transformed into reality, and especially I really hope that this will give rise to a new class of devices able really to consume a very small amount of energy and a very small amount of materials. Because this will be really the key points, the key contribution of science to develop a new world based on green energy, a new world really sustainable from material and energy point of view. So then, let's give now the podium to Professor Yury Gogotsi. Thanks.
Bruno, thank you very much for your kind introduction. I would also like to thank once again Dr. Grace for inviting me, giving me opportunity for the first time come to Vellore and meet all of you and give this presentation. Rick Smalley, who discovered fullerenes a long time ago, 1985, and worked on carbon nanotubes, being one of the founder really of the nanotechnology, nanomaterials field, used to talk that nanotechnology has two sides, a soft side where people work on polymers, proteins, DNA, use DNA, for example, to align and assemble nanoparticles, and a hard side, inorganic materials side. You just heard a very inspirational, really wonderful talk about the soft size of nano on biomolecules. I'm going to talk about the other side, which is equally important in technology, about inorganic materials, nanomaterials here. Moreover, if you work in the field of nanomaterials, particularly carbon materials, you know that it all started probably with those fullerenes discovered by Kroto and Smalley, C60, and a whole family of related molecules. That it went from zero-dimensional fullerenes to one-dimensional nanotubes. And since 2004, after Andrew Geim and Kostya Novoselov showed new physical properties of graphene, this material shown here in the middle here, pretty much attention of the world has been attracted to two-dimensional materials. And one of the reasons is that they have a whole variety of electronic properties. There are many of them. As I mentioned, we live in the time of discovery. They are very thin, they are flexible, they are very well compatible with flexible electronics everyone is trying to develop nowadays here. And actually, they have high surface area, which allows using energy storage, adsorption, catalysis, many other applications. But moreover, what is very, very important, graphene was really the first one. But already at that time, boron nitride, metal dichalcogenides, transition metal dichalcogenides, clays, oxides have been known, existed. People rediscovered them. They started to play with other 2D materials, showing they also can have useful properties. And what is important, you can build out of 2D material like brick after brick putting together, like a building a wall, and create nanostructures with combination of properties that no single material alone can deliver here. But what is more interesting, researchers realize that many materials can be made in 2D, black phosphorus, two-dimensional layers of gold, metal organic frameworks, silicene, germanium, borofin, number of other materials were created from structures which don't have layered precursors with Wick van der Waals bond, unlike a graphene or TMDs. So the community realized it's possible to make a lot of different materials as thin, few atoms thick, or even monatomic sheets here. And in 2010, working with my colleague, Professor Michel Barzoum at Drexel University, and our student, Michael Naguib, we discovered an entirely new family of two-dimensional materials, carbides and nitrides of transition metals, which no one ever expected even to be available in a two-dimensional state. And I'm going to talk to you today about these wonderful materials, at least in my opinion, and I will try to convince you that it's true, what they're good for, what they can do. And if you want to read a little bit more, this article, actually this is just an editorial with less than 2 pages of text and a few pictures, is a very good starting point to read about them. It was published about 2 months ago in ACS Nano here. But already a year before that, in 2017, CNN, which is a bulletin of the American Chemical Society, going to about 150,000 members, published an article on 2D materials going beyond graphene. And Mitch Jacoby, who is a journalist, science journalist writing this article, talked to a number of nanoscientists, asking which material are the most promising after graphene. And what is interesting, you see, MXenes are opening this article. MXenes appeared on the cover of the special issue of ACS Nano. And really, this was about the time when number of research groups and publications working on the topic started to grow up quickly from initially a limited number of groups here. So, what are those materials I'm talking about here? They're carbides and nitrides of transition metal. They're atomically thin, few atoms thick, just like other 2D materials, typically less than 1 nanometer in thickness. But they have a few features that no other known material has. One of them, first, most of them, not all, but most of them, in terminated state, are metals. They have a conducting carbide cores. And actually these large golden spheres are transition metal atoms I'm showing to you. The small dots in the middle, the black one, they are carbon and nitrogen. And I'm showing the surface termination by OH group because we produce them by wet chemical synthesis here. So they are conducting inside, but on the surface they look like clay or graphene oxide. But in graphene oxide, if you put functional group on the surface, conductivity drops by several order of magnitudes here. Moreover, their surface can be changed, modified chemically without killing the conductivity of this material. And this is very, very interesting because in case of, say, redox storage in battery supercapacitor, we can change oxidation state, we can store energy, but the material still remains conductive, making quickly charging, second charging time batteries possible here. What is also interesting, the common three groups, three flavors. We call them 2-1 structures because of 2 atoms of transition metal, 1 layer of carbon nitrogen, 3-2 structures, 4-3 structures here. So what's MXene mean? M stands for transition metal, X is carbon and nitrogen, and in ending initially taken for graphene from organic chemistry, but now used simply to show two-dimensionality, like borofine, silicene, germanine, and other materials here. Titanium-32 was the first one that Michael Naguib discovered, and in 2010 at the end, and we published this paper in Advanced Material 211. This is a cover of this first article. During his PhD study, he produced a dozen of those two-dimensional materials here. So basically, we have materials which can call like a metallic clay. Clay, water soluble because it has OH or oxygen on the surface, but having metallic conductivity. Moreover, there is something else interesting. If you are a physicist, physicists really paid very little attention to metals. Metals are boring. You cannot move the Fermi level, unlike semiconductors, where all the modern electronic is based on using semiconductors because you can apply external stimulus, like a potential, and change their properties. In MXenes, you can do the same. Those are metals, when with external stimulus, you can shift Fermi level, changing position of plasma resonance, changing their conductivity, changing a variety of their properties. So we believe it will be revolutionary, and people already come with a term, actually, Maxitronics, Hussam Al-Sharif from Kaust University, building a new type, new generation of electronic devices using those materials. So what do we have nowadays? We actually have a family with already at least 30 stoichiometric two-dimensional structures produced experimentally in the lab, about 100, at least 100 possible. So those are these monotransition metal MXenes, as I mentioned, M2X, M3X2, M4X3. But they can form solid solution. You can actually, on M side, mix different atoms. For example, vanadium and titanium, or moly and tungsten. And they form really any number of solid solutions. So it's pretty much we're facing an infinite number of compositions that we can design. We produce just in my lab, and I study now about 25 different solid solutions here. They also can be on X side. We call them carbon nitride, carbon and nitride. But moreover, we can take atomistic design to the next level and make atomic sandwiches. When one element, like moly, is in the surface, titanium is in the middle. So the surface element will largely determine surface chemistry of the material, their catalytic properties, energy storage ability, sorption, and others, while the metal in the middle, which is a bit monolayer or double layer, will largely determine electronic property of this material. And this is not all. Scientists in Sweden and Linköping University produced this type of materials where you have atomic column on one element, for example, yttrium or scandium, and 2 atomic column of another element here. Those are these materials. And if you remove one of those layers, this one, you can actually end up with ordered divacancy MXene. And we have a paper under review that adds now the 4th column to it, M5X4 structure. An undergraduate student in my group produced a new family, a subfamily of MXenes. So we are just in the beginning of the story when we, atom by atom, design an almost infinite number of novel materials here. And this is why it's exciting, and that's why it will require efforts in many, many researchers, and this is an opportunity for especially younger scientists in this room here. So, it's fine. It's good to have many materials. It's good to have bricks or Lego stones of different colors that you can build a nice structure. But we already had many materials. Do we need more? Well, as I already mentioned, they do have some properties that others don't have. And again, high metallic conductivity is truly important for many applications. People like to tell that graphene is a great conductor. Well, it's actually a zero band gap semiconductor with very few carriers, and you have to dope it, create defects to produce carriers in the material. Those materials have high density of state at the Fermi level and high concentration of carriers. As a result, if you don't want a monolayer graphene, but make a film out of graphene, what most applications really require, from reducing graphene oxide, mechanics exfoliated graphite, you actually end up with conductivity of about, say, 2,000 Siemens per centimeter. We get up to 20,000 on titanium 3C2 MXene right now. They're hydrophilic. They're soluble in water. You can take a bottle like this, put some material, dissolve, and do all the processing from aqueous solutions. Moreover, they come in every color possible. Plasmonic colors that can be used for electrochromic coatings, films, like for example, windows in Boeing Dreamliner or Airbus 380, where you can, by applying small potential, change the color, making darker here. And there are many, many other applications that we're exploring thanks to those properties. I'm going to give you a few examples today. But one thing I wanted to mention, which is really important here. If you look at the band structure of, say, this is example for titanium 2C, one of the first discovered, actually, same time discovered, but published a little bit after titanium 3C2. You see there is a high density of state at the Fermi level when material is terminated by non-terminated, sorry, with no surface here. If we change the termination, we put termination fluorine on the surface, the density of state you see decreases. But if you put oxygen on the surface and pull 2 electrons from every titanium atom, like in titanium 2CO2 structure, you can even open the band gap in this material. So this is what I mean under materials with tunable band structure. Some of MXenes, as this table shows, have actually been predicted to be semiconductors, but they have been not really much studied yet because there are plenty of semiconducting materials available in 2D. Still, I'm pretty sure we'll find some interesting properties there here. So, there have been many other properties predicted. Magnetic MXenes, we're exploring two-dimensional magnetism now in MXene. Giant Zibby coefficient means potentially useful thermoelectric material among semiconductors. Dirac fermions have been predicted in titanium 2C terminated fluorine, so cones like in the band structure of graphene. Ultra-low work function, actually work function tuning is already used in perovskite solar cells, and topological insulator, many, many others here. So, those materials have this wealth of attractive properties here. How do we make them? That's again very important because some of materials can be made, but nanomaterials in nano quantities. And this is not enough for technology usually here. So we actually take ceramic materials that Professor Barzum, my colleague at Drexel University, discovered, or he really not discovered it here. They were discovered by Novotny and others in 1960s, but he developed them as a field of materials. Those are these materials from layers of carbide, mono, double, triple layer, separated by layer of these blue atoms, which are A element. They're called max phases. So M elements are elements of this red ones that we use in MXene, X carbon nitrogen, and this blue are atoms of A element. And in my group, we have been working for many years doing selective etching. For example, removing silicon or titanium from silicon or titanium carbide to make porous carbon structure. This is how graphene was initially produced by heating silicon carbide crystals in vacuum to high temperatures removing silicon atoms and leaving just carbon behind here. So what we did, we etched A-element layers, leaving just carbide layers behind. And as a result, all these materials were produced. So we take ceramic powder, dump it in solution. Initially we use HF. Now we can use a variety of different etchants. We can etch electrochemically. We can etch in emulsion salts. And these A-element atoms, the blue ones, get dissolved. What we have now, we have MXene layers, which are still bonded to each other. You see, this picture looks like a thermally exfoliated graphite or vermiculite clay. But now they're bonded by weak hydrogen bonds because there are OH or oxygen or fluorine groups on the surface. So we can disperse them just the same way we would disperse graphene oxide, clay, or other materials, because now there is a weak bonding. One important thing is here. You cannot really easily mechanically exfoliate those materials because those not van der Waals are strong covalent or metallic bonds, depending on what kind of element is used, so we have to etch them. But because of this, we actually can produce large amount of materials. So what you see here, dark brown, it's not chocolate. This is MXene produced from a single etching in a reactor, which was designed by us, by Materials Research Center, and produced in Kyiv, Ukraine. We have 1 liter, and they made also 2-liter reactors. And what it means that you can make 100 grams of two-dimensional material. You make it in a monolayer. You can cover a stadium surface with material made from a single batch in the lab. Moreover, not only simple MXene, this is titanium 3C2, the most common one, but these atomic sandwiches like Moly2 titanium C2 with moly on the surface, titanium in the middle, can be produced as well. And this is an undergraduate student, Pavel Levek, holding about 40 grams in a petri dish of this material. And this is very important. Many nanomaterials cannot be produced in large quantities. Moreover, there are just a few of them. Aside from clay, graphene, boron nitride, moly disulfide, hardly any can be made in sufficient quantities for practical application, meaning here. Those materials are scalable, and this is very important. Moreover, what is also very useful in majority of applications is that we don't need toxic solvents to disperse them, because unlike hydrophobic graphite or graphene, they can be dissolved just in water. Because going back to your chemistry background, if there is a zeta potential which is below -30 roughly millivolt or above plus 30, material forms stable colloidal solution. So you see it near neutral pH, MXene will, and this is titanium 3C2 example, form a nice colloidal solution. So they should have high surface negative charge. They basically act as Lewis acids. And some of them go down to -80 millivolt because of all these free electrons of metals inside. And also you see 1 liter bottles with different solution of different MXenes. We can take them, and if you have a solution, you can process it in any way you want. My students bought for about $20 a spray gun for paint from a hardware store. This is one of my students holding a bottle with MXene solution. You see they're filling the spray gun and spraying it on the surface here. As a result of spraying, you can get this that you can see in the background sheet of MXene. This is actually MXene with graphene mixed for a composite material. You can see it's a 5 micron thin, but you can see that it's a freestanding and separated from the surface. And depending on amount of graphene, in this case, we had about 1 to 10,000 Siemens per centimeter. Actually, more graphene, reduced graphene oxide you add, lower is the conductivity. But we need it for energy storage purposes. And this is another student, Katlin Maleski, holding Drexel University logo sprayed coated. So again, nanotechnology does not need to be nano quantity or $1 billion worth in expenses to build it here. You see, we use ceramic powder. We use cheap acid, for example, like a HCl and fluoride salt, like lithium fluoride to etch here. and we use a $20, I'm pretty sure in India it's probably even less expensive, spray gun, the same you would basically use to paint walls or paint something else in your house to produce nanomaterials with conductivity exceeding pretty much any two-dimensional material solution processes that is known here. And this again shows that you don't need some kind of a super sophisticated equipment to do novel work and make novel materials here. But if you take a sophisticated, more expensive piece of equipment like electron microscope, a look inside, what you see, you will find flakes like this one, several microns in size, and this one follows actually hexagonal symmetry of precursor phase, max phase, and those are monolayers of MXene laying here. Here a couple of layers are overlapping, and if you magnify it further, you will see that each of them has ordered lattice, and they're single crystals, and this diffraction pattern shows. So we have flakes, which are freestanding. But what is interesting actually, they may look very similar to what you see from some graphene or moly disulfide, but you will not get a picture like that, for example, because graphene will right away drop. It's a flimsy, it's thin. Bending rigidity of MXenes, because of just few atoms thick a layer, is significantly larger, so it can actually stay suspended and keep the shape much better. And actually, it is actually pretty tough because carbides of transition metals are known and used, for example, as very resistant materials. Cutting tool, titanium carbide, tungsten carbide. So when you test, and this work was done with colleagues from the University of Nebraska-Lincoln, monolayers or double layer of MXene, you can find they're really very, very strong. And the ideal layer of boron nitride or graphene will actually show high modulus or high strengths, but those are ideals that manually removed from a single crystal. If you take reduces graphene oxide, moly disulfide, the very first one, titanium 332, already has a high Young's modulus. We tested niobium 4C now, niobium 4C3. And it has about 430 gigapascal modulus and about 30 gigapascal strengths. So those are very strong materials to add here. And we can select them by different particle sizes for different applications, and we can print them. And again, we can print even in different colors if you want, and print devices just from aqueous ink here. And for example, this is a picture of Professor Mildred Jesselhaus, grand lady of carbon science. My student printed when she passed away in 2017. Actually, it was not even printed, it was painted with a MXene automatic pen. So we can take a fountain pen, or you can take a rollerball and basically just fill it with this MXene ink and make a conductive pattern. You can see an LED light in a contact with this picture here. And of course, you can process them now just like any other solution process to the materials. You can make fibers, for example, those are bi-scrolled fibers. We can make liquid crystalline structures and align them in different ways like a liquid crystals. We can make fibers, actually draw fibers, and use them as heating elements, just like metal wires. We can incorporate these materials in polymer matrix, ceramic matrix, or metal matrix composite, use them as reinforcement, or in case of ceramic, also conducting additives, which not only increases mechanical properties, but also adds conductivity to the materials here. But what is also important, they have very exciting optical properties. I mentioned briefly in the beginning that it's actually metal, but metal with tunable properties. If you look at this UV spectrum, you will see absorption peaks, and particularly this one, it's a plasmon resonance in titanium 332. But you see for different composition, you will see plasmon resonance in different places, and this is actually give different color of materials. Moreover, for some of them, they will go much further into infrared range beyond that. And you can actually tune them by applying just 1 volt potential, negative potential, to MXene with an electrolyte between the layers. We can shift it by, in this case, it's shown 100 nanometers. So basically going from transparent film, which would be green, to blue color. and we actually go up to 150, 160 nanometer with just 1 volt applied potential. So it's a very interesting metal with tunable properties, tunable optical properties, tunable electronic properties. And as a result, of course, they start finding applications, solar cells, OLEDs, femtosecond and random lasers, plasmonics, photodetectors, many other applications. For example, just like about 2 months ago, we published a paper on using tunable work function, which is again can be changed and modified by changing surface termination. And same time, another group from Italy and Russia mixed group published another paper using actually exactly the same principle here. So it shows how quickly research is growing and propagating. I mentioned just a couple of minutes ago that many MXenes have plasmon resonance, so they basically absorb light and transform it into heat in infrared range. So they can be used as light to heat transforming materials. And big applications I found is photothermal therapy, destroying cancer cells by illuminating them with red light because, for example, titanium-32 has plasmon resonance at 780 nanometers. This is exactly positioned for red diode laser. So it's a very, very common one, and it can go much, much deeper into tissue compared to visible light, which had to be used, for example, with gold nanoparticles. Moreover, many MXenes have plasmon resonance much, much further into infrared, so infrared radiation can be used to heat it here. Many other applications. They are very good sorbent. For example, in this application, you can also absorb drug like doxorubicin on the surface, and whatever cells won't be killed by heat can be destroyed here. They can absorb urea. We're working on building artificial kidney because of this. They can be used as gas sensors. And in my group, and actually session chair shows that I just have 5 minutes left here, but in my group we primarily work on application of different nanomaterials in energy storage. This review article was actually published just last Friday, very, very recently. It's not dedicated just MXenes, it's about all nanomaterials for energy storage here. And of course, our host also published a review article just today, I discovered in the morning, looking at MXenes as new materials for also supercapacitor electrode application, our favorite topic. So I'm delighted to see research ongoing at VIT here. So let me just use a remaining couple of minutes to explain briefly why they are good for this purpose. Because what do you need to store energy? You need to be able to transfer electrons in a battery or pseudocapacitor, we call materials. And I already mentioned the outer layer transition metal, which can change oxidation state as you apply potential if you bring ions to the surface. But this material can also transport electrons in the middle layer. But between the layers, here you have a model showing water molecules, and here water molecules with potassium ions. You can transport ions. So you have basically a material that has metallic conductivity, ionic conductivity, and capable of changing oxidation state. That's exactly what you want from a good materials for energy storage. Moreover, you know, Elon Musk promised that Tesla batteries will be charged within 5 to 10 minutes when you come to a charging station. What does it mean, quick charging? It means very simple thing. You have to run very high current through the battery. And currently people use, for example, oxide material for cathodes. And even graphite that you use for anodes is not very conducting. So what happens if you run high current through a resistor? It just heats up and explodes. So this is type of material we exactly need to have very fast charging, high charging. And actually, thin film of MXene can be charged with a rate 100 volts per second. So basically in millisecond time here. And moreover, we can work also on making, for example, MXene supercapacitor and battery embedded in textile, and you're going to hear a talk today in the afternoon from Professor Thomas from University of Central Florida about energy produced, generating, and storing textiles. They can be made into transparent semiconductors. This is our work with Trinity College, with Valeria Nicolosi's group. And again, because the volumetric capacitances are high. And you can do a lot of other things. So far, this is probably the best electromagnetic shielding material available. Now we pushed actually its protecting properties above copper, but what is important for achieving about 50 decibel, we can just have 1 micron film of material instead of metal foils with about 10 to 20 micron thickness that you use nowadays. And for wearable electronic, Internet of Things devices important. We can make printable antennas for 5G internet. RFID tags with much larger distance interaction here. So there are many, many applications, and this diagram shows. Moreover, many of the fields, like sensors, biomedical application, first paper were published just about 2 years ago. So all the results I showed to you, it's not like a result of optimization of properties of material. They're the first results available. There is plenty of room for improvement. As you see now, there are already, according to Web of Science, more than 800 institutions from more than 50 countries published papers. Google patents shows more than 800 patents filed for the materials. So field is really growing, exploding. We had 450 attendees in the MXenes conference in Beijing in May this year. So to summarize what we have this new large emerging family of materials with many members, with tunable properties. Moreover, we can tune composition of material, we can tune also surface chemistry to further fine-tune the properties of the materials here. Of course, materials are new. We have more questions than answers to be addressed. There is a lot to learn. And that's again, let me repeat you, for so many different materials. It's not something any research group can do. It requires entire community. It requires people working in different fields and exploring different applications, different properties. Methods of synthesis by, for example, chemical vapor deposition. There are other structures that have been predicted to exist among nitrides, carbides, also borides. So again, there is plenty of room to explore here. And finally, I would like to show people who really did all this work. Those are my students and postdocs. And actually, research in energy storage is led by a very good scientist from India, Narendra Kura. This is this guy. He is actually currently also is my right hand, helping me to manage my lab. For example, when I'm traveling, this week, he is looking for a faculty position in India. So if you know that your institution has one, consider this guy. He is really good. Moreover, we have many, many collaborators, many people who work with us to study properties of these materials, to explore applications. I don't know everything. I am not an expert in everything, and I always try to work with people who know more than me and explore those applications. Again, thank you to many funding agencies, and you see there are US, but also many foreign entities that support our research. Moreover, we have been working for several years with Murata Corporation, which is like a Fortune 1000 company in Japan, one of the leading electronic manufacturers that is scaling up MXene technology and already has several products ready. Finally, before I end, 2 advertisements. One is we just launched recently a MS program in Nanomaterials. We are looking for excellent students willing to join. And I left a whole bunch of brochures, also not only on this MS program, but on graduate programs at Drexel in engineering in general with the organizers. I'm sure they will be available at the registration desk or elsewhere. Ask the organizer if you want one. Also, as one of the editors of SES Nano, I need to give a pitch for this journal. Those are actually MXenes, MXene atomic sandwiches are published in SES Nano. If you have a full-size article, which is really good, reporting really novel research, we certainly want to have more publication from India and SES Nano. And this is my very last slide. If you feel that it's something you may wish to explore a little bit deeper, let me give you a few references from our group. There are many other review papers. I just showed you one from Dr. Nirmala Grace published today. But this review is getting aged a little bit, but it's a good starting point going beyond the editorial I showed in the beginning. We have 2 topical reviews, and actually next year there will be 3 conferences on MXenes in China and the US, and our book just got published. So again, if you want to delve really deep into MXenes, get the book from Springer. And with this, thank you very much for your attention.
Okay, let's thank Yury Gogotsi for this broad overview of the MXene properties. So now the paper is open for a few questions. Please, are there questions? Okay.
Thank you for the new materials and new directions. I was just wondering the conductivity of these materials you have shown must be at room temperature very high at 20,000 Siemens per centimeter. But has it been measured with temperature variation? The conductivity variation with temperature?
Well, it really will depend. Oops, I don't have any extra slide to show. The metallic one will show conductivity basically increasing with decreasing temperature until about typically 50 Kelvin, where defects in this material lead to the rise, just like in 2D metals. But the ones that are semiconductor, actually you can get 7 orders of magnitude in conductivity. They will show semiconductor-like behavior with resistivity rising with decreasing temperature. And we know also by annealing inside the microscope, transmission electron microscope, we had a paper in Nature Communication earlier this year, that it's possible to remove functional groups and change it from semiconductor behavior to metal-like behavior here. So it really depends on change. What is also interesting, for titanium-32, and we don't know exactly really why, there is very, very weak temperature dependence. So if someone is looking for materials with a very stable temperature characteristic of conductivity, there is almost no change in conductivity over basically from room temperature to 100 degrees C or down to minus 100 degrees C here.
Thank you.
Professor, it's an excellent lecture.
Thank
So
you.
actually I have small questions regarding the electrochemistry of our MXenes. Since one of the best application for these MXenes are supercapacitors. How do you compare with the carbon-based materials?
Well, again, for people who are less familiar with the field, there are basically double air capacitors, or actually double air capacitor, where quick charge storage is possible because of a double layer formed on this porous material surface. And there are materials which are called pseudocapacitors that charge quickly and charge is stored on the surface, but there is a redox process. So MXenes are really redox capacitors. And they show very, very high rate and enormous, actually like an orders of magnitude, larger capacitance almost in sulfuric acid electrolyte. But we can get about 300 farad per cubic centimeter in organic electrolyte. We have a paper in Nature Energy earlier this year. So you can go beyond carbon. Still, where carbon has an advantage is in the number of cycles. Because of redox, we can go far, but not as far as carbon at the moment. We need to work on this. And one thing I also wanted to mention at the end. I was comparing MXene showing where it has advantages over graphene, for example. Not to say that graphene is useless, stop working, it will never be used. I just was trying to show where MXene can add something to existing materials, to exit properties of existing materials, and I think, so they add something to the palette. So if you need more energy, and actually even faster charging than carbon, activated carbon, MXene are good. If you need very long cycle life, carbon materials can still do better, at least at the moment.
Thank you.
Hello, Professor. It's a good opportunity for me. I hear you. So my question, you are just talking about the MXene. So did you check this study for the photoelectrochemical water splitting also? Because
we have done some HR work, again with collaborators.
Yes, sir.
With Alex Vavodish from University of Pennsylvania and a group from Stanford. They are very good. Moly carbide, actually a very good electrocatalyst. Moreover, you can use vacancies on the surface of MXene layers to place, for example, platinum atoms, and then you can do better than platinum on carbon with those materials here. There are also other groups that work on like a full cycle splitting, but oxidation of MXene under anodic potentials can actually be a danger. But for HR, definitely it's a good material, and carbides have been known to be pretty good catalyst, but in this case you just have advantage of large surface area. And one more important thing, if you take, for example, molybdenum, only edges are catalytically active. In MXene it has been shown the entire surface can work as a catalyst. So this is one of the advantages compared to diacetyl cargenides.
Okay, thank you.
Thanks for an excellent talk.
Thank you.
So my question is, you said that you can tune the Fermi energy level, right? So for tuning the Fermi energy level is very important for optoelectronic applications. So how can you do that? Is there a charge transfer, or you apply voltage?
It's largely charge transfer. Let me just explain. Actually, it's very, very simple. What happens, for example, in this case, when we do this shift here? We electrochemically change the chemistry, surface chemistry of material here, like Schwarzschild. So basically, OH will take one electron from a titanium atom. But if you change it between oxygen and H, and you can do it at minus 0.5 volt, you basically take or give away an electron. So you basically inject electron or take away electrons. So it's a very, very simple way of doing it. It's very reversible. We can run for tens of thousands of cycles. And this is one of the ways of playing with this surface chemistry.
So you can tune the 0.5 nanovolts, or what is the range you can get from it?
Or yes, roughly in that range here. But also, of course, you can change it permanently, and this was done in the case of solar cells, to basically, by changing surface chemistry, OH will actually take it to about roughly probably minus 2, but fluorine can drop it down to minus 8. So basically it's a lot. We cannot do it reversibly, at least we don't know how to do it reversibly, fluorine, hydrogen, but oxygen right in the middle, like a pound 5. So in this range, it's pretty easy to tune by, for example, like drying it, heating it, removing hydrogen from the surface, or we can get more fluorinated material by using HF. So this is a range we can play with. We published a paper in Chemistry of Material, or basically tuning work function of MXenes earlier this year.
Sir, I asked one more application-based question. The MXene supercapacitor using for the biomedical applications or implantable wearable device application is possible?
Implantable what?
Like for the pacemaker and continuous glucose parameter for sensor applications.
I'm not quite sure understand, but let me just answer as instant here. Oh, okay. I think so. I don't think why not, because two reasons. First, we do work on implantable electrodes with MXene. Titanium-32, at least titanium-32, are non-toxic and actually biocompatible, blood compatible as well. So we work with the University of Pennsylvania group on exploring like a brain electrodes and other applications. And of course, today people already make implantable battery supercapacitors. So if you package and put a device, say, inside their body, I don't think any reason why not. Again, lifetime and other properties need to be evaluated, because you don't want to remove implants frequently if you put it inside the body. But otherwise, I think it should be doable.
Yury, your EMI shielding is very interesting. Did you try to do some hybrid structures, I mean, with nickel or nickel monolayer and 3D structures, or did you also try to make some nanocomposite with polymers for efficient EMI shielding? It's very interesting value you have showed today, actually.
I have no idea where my slide is gone with EMI shielding, but okay, it's here. It's actually kind of a very interesting. This is the very first paper on MXene, 2016, published with Chonmin Koo from Korea Institute of Science Technology. This is the very first paper on EMI shielding. in Science or Nature family journal ever, because nothing was happening really in the field novel. So it was really a breakthrough in the field. This technology has already been licensed. It already is, you'll probably find it very soon in your cell phone when you buy new generation cell phones here. But what is important? Yes, it's possible to incorporate in polymer, and we do it, and actually we have done here with sodium alginate, not because it's a great polymer, because Chen Min-Kuo was passing by Drexel University, just like you visited. We gave him some sample of battery electrodes. Couple of weeks later, he sent an email telling, look, we tested this material. This is the best material ever. We tested in our lab here. So we can reach 20 decibel, which is sufficient for many applications, 99% of absorption of electromagnetic radiation or reflection, with 40 to 50 nanometer film of MXene, which is amazing. With adding polymer or increasing change in spacing, it's possible to change the ratio between absorption and reflection of electromagnetic radiation. We did not do really mixing with magnetic materials, but several groups published research. This paper has already has more than 500 citations. I think about 500 citations just last year, in the past year. So it's growing very quickly. It's about 1,000 citations now already. So people have been exploring all kind of basically EMI shielding combination with MXenes now, and we know even better materials at the moment which have not been published yet.
Okay. Oh, last question.
Professor is very famous in MXene. You are maybe pioneer of that work. Just the industrial point of view I'm asking, because carbon is well known, Maxwell is developing the supercapacitor commercially. Then how the MXene is comparable to the price as well as the energy density in unit volume?
Oh, look, there are two things. First, in energy density, it's very good actually. One of the reasons is carbon is light. And in some applications, this is an advantage. But if you have a cell phone or a battery in any device, size is really critical. So when I'm talking about volumetric, MXenes are roughly in an electrode assemble 4 or 5 times heavier than carbon. So if you get the same even 100, 200 farad per gram, you are basically like 1,000 and 1,500 farad per cubic centimeter capacitance. So the advantage is price. At the moment it's expensive, like any material produced pretty much in laboratory. But as I try to convince you, whenever you take a material with abundant element, titanium is used to paint walls again. There's probably white color is titanium dioxide, and it's the same carbon. So at large scale production, there is no reason why it should be expensive. But it's typically always go from small volume applications, value added applications to large applications. So technology for electronic supercapacitor for small devices has already been licensed, and actually entire supercapacitor application have been exclusively licensed already. But I would say supercapacitor for cell phone, absolutely reality today gives you 4 times more capacitance compared to carbon. Supercapacitor for a bus? No, not yet. 5 years down the road, 10 years down the road, possible.
Okay. So, I have the impression that the discussion can be very, very long, but it's time to stop because we have to go to lunch.
I'm standing between you and lunch, I know.
To say that it will be around in these days. So then if you want to continue the discussion, please approach him and you will get very exhaustive answer from me. So then I would like to thank Yury Gogotsi for his talk and for all the time that he dedicated to answer your question. And also I want to thank also once more Anna that for her talk of this morning. Okay, so with this, the first session, the opening session of this conference is closed, and now I suppose there are other announcements.
Yeah. Now, it's time to end the session. I thank everyone for being very patient with us. Please join us for the lunch from 1 p.m. to 2 p.m. at the Foodies.